Hardware. Hardware refers to the physical components of a computer or any electronic device, encompassing everything from the central processing unit, CPU, and memory, RAM, to storage devices like hard drives, HDD, and solid-state drives, SSD, as well as input and output peripherals such as keyboards, mice, monitors, and printers. It is the tangible part of the computer system that executes the instructions provided by software, enabling various tasks and operations. The motherboard serves as the central hub, connecting all these components and facilitating communication between them. Together, hardware and software create a functional computing environment, allowing users to perform a wide range of activities, from simple word processing to complex scientific simulations and entertainment. Let's delve into one of its most critical components, the Central Processing Unit, CPU. The CPU, often referred to as the brain of the computer, is the primary component responsible for interpreting and executing instructions from software applications. It performs the essential calculations, logic, control, and input-output operations required for the functioning of a computer. Modern CPUs are composed of billions of transistors and can execute millions of instructions per second, making them incredibly powerful and efficient. The performance and capabilities of a CPU play a pivotal role in determining the overall speed and efficiency of a computer system. At its core, the CPU performs a sequence of operations known as the fetch-decode-execute cycle. Here's a breakdown of each step. 1. Fetch. The CPU retrieves an instruction from the computer's memory, RAM. This instruction is then stored in a small, high-speed storage location within the CPU called the instruction register. 2. Decode. Once the instruction is fetched, the CPU decodes it to determine what action is required. This process involves translating the binary code of the instruction into a set of understandable signals that can be processed by the CPU's various components. 3. Execute. After decoding, the CPU performs the action specified by the instruction. This could involve performing arithmetic or logical operations, moving data from one location to another, or interacting with other hardware components. The actual execution is carried out by the Arithmetic Logic Unit, ALU, or other specialized units within the CPU. 4. Write back. The results of the execution are written back to the computer's memory or stored in a register for further processing. Modern CPUs can perform billions of these cycles per second, thanks to their high clock speeds, measured in gigahertz. Additionally, many CPUs feature multiple cores, which allow them to execute multiple instructions simultaneously, significantly boosting performance. Moreover, CPUs use various levels of cache memory, L1, L2, and sometimes L3, to store frequently accessed data and instructions, reducing the time needed to fetch them from the main memory. This improves overall efficiency and speed. In summary, the CPU is a highly complex and efficient device that handles the essential computations and operations required for a computer to function. Its ability to process vast amounts of data quickly and accurately is what enables computers to perform a wide range of tasks, from simple calculations to complex simulations. As we transition from understanding the CPU's critical role in processing instructions, let's now explore two other essential components of a computer system: memory, RAM, and storage. Memory, RAM, or random access memory, is the temporary storage that provides fast access to data and instructions currently being used by the CPU. It allows for efficient multitasking and quick data retrieval, significantly impacting a computer's speed and performance. RAM is volatile, meaning it loses its contents when the computer is turned off. In contrast, storage refers to the hardware used to store data permanently. This includes hard disk drives, HDDs, and solid-state drives, SSDs, which retain data even when the computer is powered down. While HDDs offer large capacities at a lower cost, SSDs provide faster data access and improved performance. Both types of storage are crucial for saving files, applications, and the operating system itself. Let's delve into how memory, RAM, and storage work. Memory, RAM. Random access memory, RAM, is a type of volatile memory, meaning it only retains data as long as the computer is powered on. It is crucial for a computer's performance because it provides fast access to data and instructions needed by the CPU. Here's how RAM works. 1. Temporary storage. When you open an application or a file, the data is loaded from the long-term storage, like an HDD or SSD, into the RAM. This allows the CPU to access it quickly, speeding up the process. 2. Data access. RAM allows data to be read or written in almost the same amount of time, irrespective of its physical location inside the memory. This is in contrast to storage devices that may take longer to retrieve data depending on where it is stored. 3. Memory hierarchy. RAM serves as an intermediary between the CPU and long-term storage. It is much faster than hard drives, but slower than the CPU's internal cache memory. Storage. Storage devices, on the other hand, provide permanent data retention and can be divided mainly into hard disk drives, HDDs, and solid-state drives, SSDs. Hard disk drive, HDD. HDDs use spinning magnetic disks, or platters, to store data. 1. Data storage. Data is written onto the platters using a magnetic head that moves across the surface as the disk spins. 2. Read-write operations. When data needs to be accessed, the read-write head moves to the correct position on the disk and reads the magnetic data. 3. Capacity and speed. HDDs typically offer larger storage capacities at a lower cost, but have slower read-write speeds due to the mechanical movement involved. Solid-state drive, SSD. SSDs use flash memory chips to store data with no moving parts. 1. Data storage. Data is stored in interconnected flash memory chips that retain information even when the power is off. 2. Read-write operations. SSDs can access data much faster than HDDs because there is no need for mechanical movement. They can read-write multiple data blocks simultaneously. 3. Performance and durability. SSDs provide faster boot times, quicker file access, and better overall performance. They are also more durable and less prone to physical damage. In summary, while RAM provides temporary, fast access storage crucial for running applications and processes, storage devices like HDDs and SSDs provide permanent data retention, each with its own advantages in terms of speed, capacity, and cost. Moving on from the intricacies of memory and storage, let's shift our focus to the motherboard, the backbone of a computer system. The motherboard functions as the main circuit board in a computer, connecting all the essential components and allowing them to communicate and operate together. Let's explore how it works. 1. Component integration. The motherboard houses the CPU, RAM, storage devices, and peripheral connections. It has slots and sockets for each of these components, ensuring they are securely connected and able to communicate. 2. The data pathways. The motherboard contains a network of circuits and buses that facilitate data transfer between the CPU, memory, storage, and other hardware. These pathways ensure that instructions and data can move efficiently across the system. 3. Power distribution. The motherboard receives power from the power supply unit, PSU, and distributes it to the various components, ensuring they all have the necessary power to function. 4. Biased UEFI firmware. The motherboard includes firmware, such as BIOS, Basic Input-Output System, or UEFI, a Unified Extensible Firmware Interface, which initializes hardware during the boot process and provides runtime services for operating systems and applications. 5. Expansion capabilities. The motherboard features expansion slots, such as PCIe, Peripheral Component Interconnect Express, for adding additional components like graphics cards, sound cards, and network adapters, enhancing the system's capabilities. Overall, the motherboard acts as the central hub that brings all the computer's components together, enabling them to function cohesively and efficiently. As we shift our focus from the motherboard, which connects and coordinates all the hardware components, let's briefly discuss the power supply unit, PSU, and its critical role in a computer system. The PSU is responsible for converting the electrical power from an outlet into a form that the computer can use. It converts alternating current, AC, from the wall outlet into direct current, DC, which is necessary for the operation of computer components. Let's explore the way he works. 1. Power conversion. the PSU takes the AC power from the outlet and converts it to DC power, which is needed by computer components. 2. Voltage regulation. The PSU provides different voltages required by various components, such as 3.3V, 5V, and 12V, ensuring they receive stable and adequate power. 3. Power distribution. It distributes power through a series of cables and connectors to the motherboard, CPU, GPU, storage devices, and peripherals, ensuring each component gets the necessary power to function efficiently. 4. Protection mechanisms. PSUs include safety features like overcurrent, overvoltage, and short-circuit protection to safeguard the computer's components from damage due to power issues. In summary, the PSU is a vital component that ensures the computer receives the correct power and operates safely and efficiently. Having discussed the crucial role of the power supply unit, PSU, in providing the necessary power for all computer components, let's now shift our attention to input and output devices, which are essential for user interaction with a computer system. Input devices allow users to provide data and control signals to the computer. Common input devices include keyboards for typing, mice for navigating, microphones for audio input, and scanners for digitizing documents and images. Conversely, output devices enable the computer to convey information to the user. These include monitors for visual display, printers for producing physical copies of documents, and speakers for audio output. Together, input and output devices facilitate effective communication between the user and the computer, making it possible to perform a wide range of tasks efficiently. As we move from understanding the roles of input and output devices, let's delve into another vital component that greatly impacts the visual performance of a computer, the Graphics Processing Unit, GPU. The Graphics Processing Unit, GPU, is designed to handle and accelerate the rendering of images, videos, and animations. Here's a brief overview of how it works. 1. Parallel processing. Unlike the CPU, which is optimized for single-threaded performance, the GPU has many smaller cores that work simultaneously to process large blocks of data in parallel. This makes it highly efficient for tasks like rendering graphics and performing complex calculations quickly. 2. Rendering pipeline. The GPU processes graphical data through a series of stages known as the rendering pipeline, which include steps like vertex processing, geometry processing, rasterization, and pixel processing. These stages transform 3D models into the 2D images displayed on the screen. 3. Memory. GPUs have their own dedicated memory, known as VRAM, Video Random Access Memory, which stores textures, frame buffers, and other graphical data. This allows for quick access and manipulation of graphics data, further speeding up rendering tasks. 4. Shaders. Modern GPUs use programmable shaders, which are small programs that run on the GPU cores to perform specific tasks like lighting, shading, and texturing. This flexibility allows for more advanced and realistic graphics effects. By offloading graphic-intensive tasks from the CPU, the GPU enhances the overall performance of a computer, particularly in applications requiring high-resolution graphics and real-time rendering. Shifting our focus from the GPU that handles graphical processing, let's now take a look at another crucial component, the Network Interface Card, NIC. The NIC, also known as a network adapter or network card, is a hardware component that enables a computer to connect to a network, such as a local area network, LAN, or the Internet. Here's a brief overview of how it works. 1. Data transmission. The NIC converts data from the computer into signals that can be transmitted over a network. For wired connections, this involves converting data into electrical signals sent through Ethernet cables. For wireless connections, the NIC converts data into radio waves. 2. MAC address. Each NIC has a unique identifier called a Media Access Control (MAC) address, which distinguishes it from other network devices. This address is used to ensure that data is sent to the correct destination within the network. 3. Network protocols. The NIC follows specific protocols, like TCP/IP, Transmission Control Protocol, Internet Protocol, to ensure reliable and accurate data communication over the network. 4. Interfacing with the motherboard. The NIC interfaces with the motherboard via an expansion slot, such as PCIe, or is integrated directly into the motherboard. It communicates with the CPU and other components to manage data transmission and reception. Overall, the NIC plays a vital role in enabling network connectivity, allowing computers to communicate, share resources, and access the Internet efficiently. In conclusion, hardware forms the backbone of any computer system, encompassing a variety of essential components that work together to ensure smooth and efficient operation. From the Central Processing Unit, CPU, which executes instructions, to memory, RAM, which provides fast access to data, and storage devices, which retain data permanently, each part plays a pivotal role. The motherboard serves as the central hub, connecting all components, while the Power Supply Unit, PSU, ensures they receive the necessary power. The Graphics Processing Unit, GPU, enhances visual performance, and the Network Interface Card, NIC, enables connectivity. Together, these components create a balanced and efficient system, enabling a wide range of tasks and applications. Please remember to subscribe, like the video, and share it with your friends. Your support is greatly appreciated.